Swayam Prabha. Digital India. Educated India.
So it's a great honor for us to have with us Professor Jaikumar Radhakrishnan. Jaikumar is a distinguished professor at ICTS in Bengaluru. ICTS stands for the International Center for Theoretical Sciences. And Jaikumar works in the mathematical foundations of computer science. So he's a theoretical computer scientist. So a quick word about him. So Jaikumar obtained his BTech in computer science and engineering from IIT Kharagpur in 85 and his PhD from Rutgers in 91. He then joined the TIFR in Bombay in 91. In 24, he is now at the ICTS in Bengaluru. So he has won several awards, one of which is the Shanti Swarup Bhatnagar Award. So over to Jaikumar.
Yeah, so I'm a theoretical computer scientist. I'll tell you something about the pigeonhole principle, which you might have seen. So this is a combinatorial principle. It looks like an obvious thing. And sometimes this obvious thing helps us establish rather deep things, okay? So we will start with simple examples. Please ask me if something is not clear. And as Professor Dhar said, there is no fixed real agenda, but I'll of course be very happy to tell you something that you did not know before. So the first half an hour or so will be things that you either knew or could have guessed anyway. Okay, so let me start slowly. So here's a question. So these are things which look like puzzles. Yeah, so you have a box, yeah? And you're not one of those careful people who keep matching socks in pairs and, you know, tie them together. So it's a box, it has some red and blue socks, and you go in and probably watching the match, and you want to, yeah, it's very dark, and you pick up some number of socks. And you come out of the room and you're ready to wear. Let's assume that there are no left socks and right socks, okay? So if you get 2 red socks, you're happy. If you get 2 blue socks, you're happy, yeah? And you can wear them, okay? So now, how many socks must you pick so that you're assured that you have at least one matching pair? By matching pair, meaning a pair of the same color, yeah? 3, yeah. If you pick 3, well, 2 of them have to be of the same color, yeah? All right, okay, so very good. So, yeah. So the next question, Okay, so here is a statement that here's a class which has 13 students. Okay, lucky number. Yeah, so 13 students, and then it must be the case that there are 2 students in the class whose birthdays fall in the same month. Is this obvious? Is this true? Yeah, and why is this true? Sorry, because there are only 12 months and there are 13 students. Yeah, 12 months, 13 students, so some 2 of them must fall in the same month. Okay, so yeah, so the principle that is behind these statements is called the pigeonhole principle. So what is the pigeonhole principle? Sorry, n plus 1. Yeah, if n plus 1 balls are placed in n bins, then so there are n bins, n plus 1 balls of all of the same color, we don't care, yeah? And they're placed in n plus 1 balls, placed in n bins, then can you complete this sentence? Yeah, sorry, yeah, at least one of the, very good, yeah. Yeah, maybe I should, yes. Yeah, okay, so n is not 0, yeah. N is at least, yeah, 1. So maybe you have 5 balls, only 4 bins, yeah. So in this example, what were the bins and what were the balls? Students were balls and months were the bins. You got the idea? Yeah, the months were the bins into which the students were being placed. Yeah, there was 1 bin for each month, the January bin, the February bin, and this. And there were 13 students, and we were placing them into bins depending on when they were born. And we know that if this principle is true, there is some bin which has, okay. And in this case, what are the bins and what are the balls? Colors are? Sorry, finish your sentence. Colors are? Colors are the bins. So how many bins do we have? 2. 1 corresponding to red and 1 corresponding to blue. And if you picked 3 balls, they are placed in the bins, meaning they have the color. So one of the bins must have 2 of them, okay? So yeah, maybe one way to think about all these things is that you think of the balls, yeah, I'm drawing them round, yeah, and these are the bins. And so here there are n plus 1 of them, and here there are only n. And whenever n plus 1 things are stuffed into n things, there must be at least one of them which has 2. Okay, yeah, good. So here's a So I give you n plus 1 numbers. Yeah. So is everybody's comfortable with n? Like, would you prefer I call it 17 and 18? N is okay, right? Yeah, yeah, okay. So there are n plus 1 numbers. Yeah. And the claim is that if you have n plus 1 numbers, the difference between some two of them will have to be divisible by n. Let's consider the case n equals 2. Yeah. Oh, sorry, are they distinct? Is that what you're? No. They're just some n plus 1. Oh, when I say numbers today, I mean natural numbers. Yeah. Let's even say non-negative, positive numbers. Oh, sorry, yeah. I consider 0 as divisible by n. Yeah, if two of them are the same, okay, let's assume they are distinct. Okay. So n plus 1 distinct numbers if you want, but otherwise, yeah, if they are all the same, then their difference, any pair, arbitrary numbers. Yeah. Sorry, I was going to say n equals 2. Yeah. If there are n equals 2, what is the problem we are trying to think about? A1, A2, A3. There are 3 numbers. Why is it that the difference of some pair is divisible by 2? Okay. Yeah. So if you see it, raise your hand. And yeah. Why is it that when you have 3 numbers, the difference of some 2 of them must be, yeah. So yeah, please give it a thought. I give you 3 numbers. Yeah. Yeah, if you have 3 numbers, then some difference of some 2 of them, some 2 distinct of them. You can't subtract A2 with itself and give me an answer. Yeah, sorry. Yeah, tell me. Yeah, so why did you say probability?
Just when you pick a number, it's either odd or even the possible. So when among these numbers, you'll have either 2 odd numbers or 2 even numbers.
Yeah, so that's the end of the thing, right? What is this probability business? Yeah. Okay, you were going to say something else.
There are 4 cases.
Huh?
There are 4 cases. All are odd, all are even.
Uh-huh.
There are 2 even, 1 odd, 2 odd, 1 even.
Okay, yeah.
In any case, you can pick 2 odd or 2 even and the difference will be even, which means it's divisible by 2.
Yeah. So you have A1, A2, A3. Yeah. What are my bins? Yeah. What are my bins? Okay. Good. Is everybody with me? Yeah. You've been given 3 bins. These we invent. Okay, so part of the art of applying the Pigeonhole principle is to imagine everything as balls and boxes. Okay, yeah. So of course, one writes it like this and you don't see any balls, any bins. But okay, n equals 2. Yeah, at least you can match n plus 1 and n plus 1 and realize that it must be the same. But anyway, so you have 3 balls and you have 2 bins. And how do I decide to put A1 in this or this? When do I draw a line? Yeah, take A1 and where do I connect it to? That's right. So if the remainder is 1, I connect it to odd, and if the remainder was 0, I would have connected to 0. Okay. So this way I shoot 3 arrows depending on the values. Okay, there's no probability. It is either it connects to this or connects to that. Is that okay? Yeah. Then what do we know? Yeah. 2 of them are odd or 2 of them are even. Now, if you have 2 numbers which are even, what can you say about their difference? And so it is divisible by 2. If 2 of them are odd, what can you say about the difference? Okay, so wonderful. All right. And so this was a special case. What would you do when the numbers, Yeah, so I would just like you to think. Much of the answer was sort of heard in this room already. So you have n plus 1 numbers. Yeah. So now let me do the hard work for you. A1, A2, AN. These are the balls. What are the boxes? Remainder when divided by? Remainder when divided by n. Okay, good. So how many boxes? N. What can the remainders be when you divide a number by n? 0 to n minus 1. Yeah. Very good. Yeah. 0 to n minus 1. Yeah. How many are there? N. Okay. Yeah. You start at 0. Yeah. 0 to n minus 1. There are n of them. Yeah. And there are n plus 1. Yeah. N plus 1. N plus 1. Yeah. All right. And when do we connect them? You had almost an algorithm. You take A1. How do you decide to put it in a certain bin? Divide by n and then? Yeah. So if A1 gives a remainder 2 when divided by n, you connect it to this box. Yeah. A2 is already divisible by n. That means it gives remainder 0. Yeah. Then what do we know? Two of them are connected, say AI and AJ. I and J distinct are both connected to the same remainder R. AI and AJ are both, when divided by n, they leave the same remainder R. What can you say about their difference? It will be, so it will be divisible by n. This is something that Shiva said, right? If two numbers are divisible by 7, 2 days of the year are, yeah, this divisible by 7, or they leave the same remainder when divided by 7, then those two are the same days. That is, they must both be Wednesday or they must both be Thursday. I suppose that's what he said. Yeah. Okay. So yeah, so we are done. Is everybody okay with this statement? That if you get n plus 1 numbers and you can always find two numbers whose difference is divisible by n. Yeah, yeah. Okay, sorry. Yeah. Problems are probably too simple. Let's. So you have a party. Is it? Yeah.
Yeah, everyone's here.
No, it's okay. Please take your time. Yeah. So there's a party with n persons. Yeah, and they all show up and they shake hands. Yeah. So okay. So let's try. So there are n people. They come. Some of them shake hands. Some of them don't shake hands. Okay. But in the end, they count. Okay, let's assume we don't shake hands with the same person twice. So it was a little embarrassing. Yeah. So So yeah, so you you go shake hands, but in the end, everybody counts how many times they have shaken hands. There might be these like antisocial, didn't shake hands at all. And there's somebody who's shaken hands with everybody. If somebody has shaken hands with everybody, how many times did they shake hands? N minus one, okay, yeah, so good. So now, yeah, so, yeah, maybe I should say N is at least 2, yeah, yeah, so if there are not even 2 people, it's not very easy to shake hands, yeah, so yeah, so you have these N people, and some of them shake hands, some of them don't shake hands. Yeah, this pair didn't shake hands at all. Yeah. And so, but then what are we counting? Okay, so is this sort of a thing already? If I use the word graph, it's okay with you? Yeah, okay. All right. So these are nodes, vertices. Yeah, these are vertices of the graph. There are n vertices because there are n persons, and we connect them if they shake hands. So we draw an edge between them if they shake. Okay, good. Now, the number of edges coming out of a vertex is called, okay, is the degree of the vertex. Okay, but doesn't matter. Now, here, this person has shaken hands how many times? 3 times. And this person? 3 times, yeah? Good, yeah, there's a huge number of 3s. This is 2, yeah? And this is just 1. But no matter how you draw these lines, there will always be 2 who have shaken hands the same number of times. Yeah, so, yeah, whichever party you go to, at the end of the party, you ask everybody, how many times did you shake hands? There will always be 2 people who will shake hands the same number of times. Okay, now why is this true? Sorry, what are the balls? What are the bins? Yeah, we'll come to that. Yeah. So yeah, what are the balls? What are the bins? We want to find 2 persons who have shaken hands the same time. Yeah, 2 persons, and if our past experience means anything, the persons should somehow be balls or bins? Balls, okay, good, that's good, everybody is good. Persons should be balls. What are the bins? Yeah. Number of times they shake hands, yeah. So the number of times they can shake hands can be anything. What possible numbers are there? That 0 to n minus 1, yeah. So let me draw the picture for you. So these are the n persons, huh? Not n plus 1, n persons, yeah. So n persons, and then there are people who have shaken hands 0, only once, twice, up till n minus 1. How many numbers are here? N. And here, n. It doesn't seem to quite work, right? Yeah, yeah, I'll come to that. Yeah, no, so, good idea. Balls and bins are ready. But there are n balls and n bins, yeah? Luckily in this problem, there were n plus 1. We also started at 0 here, but it was n bins, n plus 1 balls. Here there are n balls. We would have liked n minus 1 bins to just dispose of the problem. It's not quite n minus 1. So what's the problem? Yeah. Yeah. If somebody has an answer, yeah, go ahead. Sorry, the number of hands. Oh, you're saying. No, yeah. We have gone only, if you shake everybody's hands, it is n minus 1. Okay? Yeah, yeah. I'm not cheating, yeah, at the moment. Yeah, I'll come to that. No. So if somebody, yeah, no, I want you to think. Yeah, I'll come to that. Yeah, please thinking. Till more hands are raised, I will wait. Yeah. Are all these numbers possible? Yes. Okay. Yeah. Want to say something? Somebody? Yeah. Yeah. Go ahead. Yeah.
So first, zero people have zero handshakes, and then two people shake the hands. They both go to the same bin, and then if one person decides to shake with another person, then that person will go to another bin, but that person who hasn't shaken previously, he will replace him to a same bin. So each succeeding handshake, you will always replace someone to your bin, while you yourself go to a higher bin.
Yeah, so how do I apply the pigeonhole principle? Yeah, one second. Yeah. So you're giving me some sort of an algorithm. No, let me try to understand. Yeah, you're giving me some sort of an algorithm to find the two people. Yeah, so you say he shook a hand. Maybe he never shook a hand with anybody at all. Okay, so there are many cases to consider, but I would like a crisp argument, a crisp combinatorial argument. Yeah, go ahead.
Both 0 and n minus 1 are not possible at the same time. Because if you shake hands with everybody, the other person also shook hands with you. So you can't just shake hands with 0 people if n minus 1 is 1.
Yeah. So did everybody hear that? Yeah. So what's the solution? We somehow have to discard one bin here. Yeah. So in any party, yeah, can this bin and this bin both have people? Yeah, that's what you said. Huh? If both can't have, why? Because if there is somebody who's been standing aloof, then nobody could have shaken hands n minus 1 times. So in any party, either the bins are this or, is this clear? Yeah, it's a little twist on our old formula. Yeah, so if you take any party, either the bins are this till n minus 2. Yeah, that happens when there is somebody who has refused to shake hands. Yeah. On the other hand, making it sound like India-Pakistan match. Yeah. Yeah. So yeah, and if everybody has shaken hands, then 0 is not a possibility because everybody has shaken hands. Is this okay? Yeah, and we are done by the pigeonhole principle. Okay, so I'll go on to the next problem. Yeah, so sorry, it's all probably looking childish at the moment, but it'll become interesting. Yeah, trust me. So still in the party mood. Yeah, let me explain. It's not, I mean, it can mean many things, okay? So you have a party, how many people? 6, okay? Now, every pair, yeah, of persons in the party, it's possible that they knew each other from before. Or they are complete strangers having first met in their life in this party. Okay? So there are two possibilities for every pair. Either they are acquainted with each other, they know each other, or they don't know each other. Okay? Now, in these 6, I want 3 that either mutually know each other. That means every pair of them, yeah, were acquainted from before, or every pair of them were not acquainted. So this has been discussed already? No, okay, yeah, okay, so. Right. So, all right, so maybe since you like this, can I, so there are 6 here, I hope, no. 6, yeah, and I draw a straight edge. There are colors here, but I don't know how well they work. So, yeah, so tell me if you can tell the difference, yeah. So, a straight edge means they know each other, okay? And I'm drawing it yellow and wavy. So, a yellow edge means they didn't know each other, okay? So now, if I take these 6, every pair is either a straight edge or a wavy edge, yeah? Straight edge or a wavy edge. And what are we looking for? What are we looking for? 3 people or, but tell me in the language of graphs. So, yeah, that means I want 3 vertices such that
One triangle of wavy lines or one triangle?
want a degree 3 node.
degree 3 node, no, good. So a degree 3 node would mean a person who knows 3 other persons, a popular person, okay? Yeah, that's not what we want. Sorry, yeah, so how do you read this question? There are 3 persons, yeah? So it is a triangle which is made out of solid lines or a triangle which is made out of, all 3 edges should be wavy. Yeah, don't show me a triangle which has 2 lines straight. And when you have 6 persons, try to draw wavy lines and straight lines whichever way you want. There will always be a triangle that has straight lines or a triangle which has wavy lines. Okay. Would you like to try some examples, like draw 6 vertices, just draw straight lines and wavy lines, and see whether you always find either a solid triangle or a wavy triangle. Okay, is this space okay? Okay, so yeah, while you do this, just in the end, we have to do some pigeonhole apparently. Yeah, because that's what I said. So how many edges are there in this picture? How many edges are there? Sorry? How many total? Wavy and solid, both included. How many edges are there? There are 6 vertices. 15. How did you do that? Combinations.
There are 6 vertices, and you need 2 to form a triangle.
Yeah.
So out of the 6 vertices, I can choose 2 vertices and form.
So it is 6 choose 2. Is this the word you use? 6 choose 2. Yeah. 6 choose 2. Yes. 6 C2. Okay. Yeah. 6 choose 2. So it is 6 times 5 divided by some 2 factorial type of thing. Yeah. So it is, what did you say? 15 edges. Yeah. And each edge is either straight or wavy. Is that right? Yeah.
Can be possibilities with no triangle.
No triangle at all. So, yeah, 1 second, let me try. 1, 2, 3, 4, 5, 6. Yeah, tell me which are your solid edges. Yeah, you had an example. Which are your solid edges? sorry, please think. Yeah? So there are 15 edges. Each edge could be wavy or solid. Yeah, wavy or solid. Okay, yeah. Sorry, you still have an example or you misunderstood the problem? Yeah. Yeah, this is, yeah. So there are 15 edges. And each of them could be either solid or I'm calling it wavy. Yeah, wavy, yeah. Yeah. Good. Yeah. Okay, so what do we know? If we have 15 edges and each of them is solid or wavy, then what can we say about edges of the same kind? 15 edges, two types, solid or wavy. There must be at least, sorry, 6 of the same kind? 15, 7, 7, even more? Good, yeah. So if you have 15 and you have to pack 15 people in two boxes, yeah, sorry, sounding very cruel, but yeah, so 15 balls in 2 boxes, then one of the boxes must have 8. Yeah, one of the boxes must have 8. Yeah. So, okay. Yeah. So let us focus on the edges which are of the same type. Yeah. Let us say there are 8 wavy edges. Yeah. At least 8 wavy edges or 8 solid edges. Yeah. So let's consider the case when there are 8 wavy edges. Is it true that whenever you draw 8 wavy edges, there will always be a triangle? Then we would be done. If it was the case that any graph on 6 vertices with, we are not thinking about the solid edges, only the wavy edges. Any graph with 6 vertices and 8 wavy edges will always have a triangle. Is it true? No. Why? How many edges can you have without a triangle? You want to draw a graph, yeah, without a triangle. You can draw 7. Yeah, but I mean, somebody said 9. Yeah, how would you do that? Sorry, but there might be a, I don't want a triangle. Yeah, so can you construct a graph with 9 edges which has no triangles? Not possible. Can you have 9 edges and no triangles? Yeah, sorry, please try. If you have 9 edges, 6 vertices, 9 edges, and no triangles. It is possible, okay, yeah. Is it possible to have 9 edges in a graph without any triangles? No, yeah, so only wavy edges are being drawn, solid edges are out. Can you put 9 wavy edges on 6 vertices so that there are no triangles? 8 would have been enough for us, but yeah. Yes? I want to put 9 edges without any triangles. Can you see how to put 9 edges here so that there are no triangles? I don't know if I did everything correctly, but whatever. Yeah, I don't know what you can see in this, but yeah. Yeah, you prefer straight. Yeah. Yeah. So how many edges are there? How many edges are there in this graph? Sorry? I mean, how many edges are there in this graph? Sorry, why did you count 11? This vertex has 3 edges, this vertex has 3 edges, this vertex has 3 edges, and all edges are counted. So what's the number? 9. Is there a triangle in this graph? Oh, you can see a triangle. Yeah. Now, how do you say that there is no triangle? I mean, okay, no.
Each one to this side connects to each one to that side, but there is no interconnection in this side.
A triangle has how many vertices? 3. How many sides does this graph have? 2. So 2 of them must be because of the pigeonhole principle. Okay, yeah. So if you had 3 vertices, I'm sorry, I'm making a big deal of a small thing, but I want you to train yourself to say pigeonhole principle when your argument is pigeonhole principle. I don't want a long English sentence when the argument is a pigeonhole principle, okay? I mean, sorry, after the class you can do whatever you want. I'm just saying, let us focus ourselves. This graph doesn't have a triangle because if there were 3 vertices, 2 of them must be from the same side. And if they are from the same side, they are not connected by an edge. So how can that be a triangle? Is that okay? So what is the message? That this plain old pigeonhole principle which I was suggesting was actually misleading. Yes, one of the edges is very popular. Like wavy edges are very popular or straight edges are very popular. 8 of them are of the same type, okay? But that doesn't give the reason why there is always a triangle. A wavy triangle or a straight triangle, okay? Good, so I would like you to think a little bit more. So I'm going to erase all this because all this was bogus, okay? I'll tell you, I'll tell you something about this bogus thing, yeah. All right. So I misled you, took you to the wrong side, but there's still pigeonhole involved. And what is the pigeonhole? There are 5 other vertices. 1, 2, 3, 4, 5. And this vertex has edges to all these 5 vertices. Each of the edges is either wavy or solid. There are 5 edges out of those vertices. Each of those edges is wavy or solid. There are 5 edges out of that vertex. Each of them is wavy or solid. At this point, what? Okay, and what does the pigeonhole principle tell us? This has 5 edges. Yeah, I'll wait for your answer. This vertex has 5 edges. Each of them is either wavy or solid. Then there must be 3 are wavy or 3 are solid, okay? So, yeah, maybe let's consider the case where 3 of them are wavy. Yeah, and it is solid to the others. Maybe it is also wavy to the others, but there are at least 3 vertices that are wavy. Then what happens? How will you get a wavy, what should happen so that you get a wavy triangle? If any pair of these is connected by a wavy edge, then we would get a triangle. And if they were all connected with a solid edge, then they are the triangle. Thank you. Yeah. Did this make sense? Once again, Here is a vertex which has how many edges? In all, wavy plus straight. 5. And the edges come only in 2 types, wavy or solid. So 3 of them must be of the same type, at least 3. Yeah? Focus on those 3. And look at the tips. If even one of the tips, one of the pairs is connected by a wavy edge, we are done. Why? This, and this would form a triangle. And if all of them were solid, that means this was solid, and this was solid. That's a triangle. Okay. So it's not the case that the triangle has to be in the most popular type. For example, suppose the graph was our counter example. That is, sorry, you prefer straight. All these were straight. How many straight edges? Sorry, I connect all of them. I've not done a complete job, but whatever. Yeah, 9 straight edges. And how many wavy edges? Let's say the remaining are wavy edges. So how many wavy edges do I have here? 6. And how many straight edges? But is the triangle in the most popular type? What is the most popular type here? Straight. But it is the less popular thing which has the edges. Okay? So that's why what I said initially, where I somehow greedily went for the most popular type and tried to look for something there, did not quite work. Because sometimes, even though the theorem is true, it turns out that the triangle actually is formed in the less popular type of edges. Okay, is this okay to everybody? Yeah. So this theorem is a baby theorem in a big area called Ramsey theory. Okay, but yeah, so you can look it up later. Yeah. So now I should move on. So I go on till 12:30 or? Okay. So yeah. So you have these numbers 1 to 16. Yeah, 1 to 16. And we arrange them in some arbitrary order. How many ways are there to arrange 16 numbers in an arbitrary order? 16 factorial, okay? So I arrange them. Let me call it A1, A2, till A16, yeah? So you can, this is a permutation of 1 to 16, yeah? Good. So, or this is a sequence. Okay. So let me take an example. So I've no, I'll put it, yeah, that's okay. That's okay. Thank you. No, it's okay, it's okay. Yeah, I just need to. Okay, so this is a permutation of the numbers 1 to 16. Yeah, and this is a sequence. Yeah? Sequence, and I'm going to tell you what's a subsequence. Subsequence is just these numbers, but you know, yeah, 12, 14, 16, 1, 11, 6, and 9. Okay, so these were the numbers 1 to 16. Some of them I have kept and pulled them down, but kept them in the same order. I'm not allowed to jumble them. Okay, so then this is the sequence S, and this is the sequence S prime, but S prime is a subsequence of this sequence. Yeah, you had a question.
So then the Pigeonhole principle, it's applicable for all n plus 1 and n such that n is less than n plus 1.
That is true.
For any n less than n plus 1.
Yeah, so so yeah, I don't know his name, but there was a suggestion that I somehow was very rigid in my definition of a pigeonhole principle, that if there are n plus 1 balls, they needed to be put in n bins, then some bin will have at least 2. But suppose n plus 1 balls was put in n minus 2 bins instead of n bins, still there will be 2. Yeah, so maybe I should write down, so if m balls are placed, sorry, I'll come to that, yeah, placed in n bins, then there is a bin with so if m balls are placed only in n bins, think of m as a large number, n as a small number, then some bin must have at least how many? At least? Well, that depends on, if m is less than n, m minus n mod n. I mean, m minus n mod n could be 0, and then this statement is not saying much. No, if there are 4 queues here, yeah, 4 queues, and this class of 38 has been put, yeah, made to stand in these 4 queues. One of the queues has to be long, right? Can all queues be very short? How long should one of the queues be? At least 10. One greater than? Okay. If there are m things which have to be put in n, some bin must have at least m over n. At least m over n. You said ceiling because it's an integer. So it has, if it is m by n, it has to be an integer, at least m over n. Okay. So, and what about? M, I know. There are only m balls. Can all the bins have m? So at most m minus 1. M minus n. Sorry? What did you say? Just say it twice. I didn't hear. M. M is true. Yeah. I mean, nothing wrong in writing the answer M, and you can, yeah, you can litigate and say that I need full marks for that. But that's, yeah. What's the best answer? M minus 1 is also at least. Yeah, yeah. So M balls are placed in N bins. Yeah. No. M is correct, but better answer. So suppose I have 5 bins and 20 balls. Okay. What can you say? Like there must be some light bin, right? Can all the bins be very heavy? How light can you promise that the bin will be? If I have 20, let me say it again. Sorry, I created a lot of confusion. 20 balls, 20 balls, 20 balls, 5 bins. Yeah? And I want the lightest bin. How light will the lightest bin be? Guarantee. Like, can I always promise that there is a bin with 0 balls?
If you want to make it as light as possible.
I don't want an arrangement. I want to make a statement that I want you to give me a sorry, just listen to me. Yeah, yeah. I want you to give me a number k so that there is always a bin with at most k balls. At most k balls. Yeah. So if I have 20, sorry, how many bins was I? 5. Okay. Yeah, I forgot. Yeah. So I have 20. Can all the bins have 6 balls? Yeah. Can all the bins have 5 balls? Can all the bins have 4 balls? So what should I say here? Sorry. I mean, this is a totally obvious statement, but I don't know how I managed to confuse you. If there are m balls that are placed in n bins, can all the bins have more than m over n balls? If all the bins had more than m over n balls, the total number of balls would become more than m. Yeah? So there must be some bin which has at most. When I write at most, I don't mean strictly less. M over n or less. Question.
But this is taking the worst case, right? Like there could be a case where one bin is having, like 3 bins are having 0 balls and the last bin is having all.
All of them, yeah.
But then at this case, that actually
Give me an example. You said you had one bin which had 3 bins which had how many? Sorry, 3 bins which had how many? 0. 0, 0, 0, and the last one? 20. Is there a bin with, what is m over n in this case? 20, 5. Is there a bin with at most 5 balls? Yes or no answer. Is there a bin with at most 5 balls? So how have you contradicted this statement? No, no. There is a bin with at least 5 balls. There is another, sorry, I didn't mean the same bin. All right. Okay. Yeah. Question.
In case of n not being divisible itself, then not being n not being a factor of itself, we have to round up the
Okay. But that at least, that statement was still true. You could say even a better statement. But since things are integers, when some number is at least m over n, yeah, if you say that, you got at least 2.5 laddus, what does that mean? You got 3, at least 3, right? So that is implicit in this statement. You had a point.
Why is it ceiling for at least and floor for most?
No, yeah, I don't want to start a fight between them, but each of them individually is true, right? Yeah, that, I mean, yeah, I don't know how to answer that question. Yeah, best, yeah, I would just leave it at m by n, and the rest you conclude because things are integers. Okay. 21 balls. Yes, 21 balls and 5 bins. Yes, 21 balls, 5 bins. 4.2. So there must be a bin with 4.2. If it is at least 4.2, then the number must be, because it's an integer, the number of balls in a bin has to be, yeah. Maybe, yeah, okay. So let me just finish this question and then we will stop. Yeah, okay, good. Yeah. So very good, yeah. Please think about this. I don't think it's a question of, I'm giving you some great wisdom, okay? It's just that you are not used to the words at least and at most, okay? I think that is the problem. Just, yeah, okay. So now, yeah. So a sequence, a subsequence of this sequence is said to be monotone if it is either increasing or decreasing. So for example, 12, 14, 16 is a monotone subsequence, okay? Sorry. Yeah. Sorry, this was already increasing. So 12, 7, 2, 1. So I take 12, 7, 2, 1. It's a subsequence and it is decreasing. So this is an increasing subsequence and this is a decreasing subsequence. Okay, so I'll leave you with this problem. Yeah. It has neither an increasing subsequence of 5 elements, nor a decreasing subsequence of okay, so over lunch, take these 16 numbers and you have to arrange them, and when I look at that sequence, I should not be able to find an increasing subsequence of length 5. I should not even be able to find, I mean, one way to avoid increasing subsequence of length 5 is doing what? Suppose I don't want any increasing sum, just write it in descending order. But if you write it in descending order, then I have a subsequence of length 16. Yeah, a sequence is its own subsequence. So it's a decreasing subsequence of length 16. You have to jumble up these 16 elements so that I can neither find increasing nor a decreasing. And the theorem that we will do after the break be sorry. Yeah. So arrange 16 numbers so that you don't get a good trend, an increasing trend or a decreasing trend. The biggest trend you can get is 4. Yeah, you should not be able to get a long trend. However, the theorem says that the moment you go from 16 to 17, then there is no such construction. There will always be either an increasing subsequence of 5 elements or a decreasing subsequence of 5 elements. And this theorem has a name. It's called the Erdős-Szekeres theorem. Okay, the Erdős-Szekeres theorem. Okay, so far we have done applications that are sort of, you could have done it if I had given you enough time. This also, I would like you to do it, but I will help you do it in the next session. Okay, sorry to go over time, and yeah, so probably you'll have a hurried lunch. Thank you very much.